to talk about modeling wave-ice interaction, and in particular, the wave-triggered breakup of the sea ice. So, okay. So sea ice is a major component of the climate system, and in the past decades, its extent in the Arctic has been diminishing alarmingly. And between the open ocean and the continuous ice cover, there is a transition zone occupied by flows of various sizes. And this region is called the marginalized zone, and it delimits, it's a region where the ice is really impacted by wave activity. And recent trends show a widening of the marginalized zone, exposing ice flows to wave activity along deeper transects. Energetic waves can break the ice, as we have just seen, and as smaller flows are more susceptible to lateral melt, it can become a feedback loop, a positive feedback loop of breaking and melting. There have been numerous remote sensing observations of flow sizes, but unlike what Ellie just showed us, they are not usually connected to wave activity, making it hard to establish a link between waves and the reshaping of the flow size distribution. Additionally, direct instrumented observations of the breakup are scarce, making numerical modeling a valuable tool to improve our understanding of this process and improve the reliability of global climate models. To study wave-driven sea ice breakup, I've built a numerical model that allows wave propagation into an array of floating flows. This model represents a two-dimensional domain with homogeneous subdomains, either ice-covered or ice-free. It relies on linear water wave theory, which allows us to describe the fluid motion with a scalar velocity potential, a solution of a Laplace equation. The model has a finite depth, and ice flows are represented as floating viscoelastic plates of constant thickness located in space with known length and positions. And finally, we follow the model with a time harmonic plane wave of prescribed period and amplitude. The first thing baked into the model is wave scattering. It solves for the steady state reflection and transmission of a wave by a flow edge by ensuring continuity of pressure and velocity when crossing the boundary between ice-free and ice-covered regions. The propagating wave is expanded onto wave modes, satisfying appropriate dispersion relations. And by assuming knowledge of the incoming wave modes, we can derive the outgoing wave modes and link the two with a linear map. In practice, the two edges of a single flow are coupled together, and this flow is coupled to its two neighbors, which by recurrence leads to a large sparse linear system. Because of the sparsity of its system, it scales up nicely, and the model can determine scattering with a large number of flows without any issue. The system can be solved directly when prescribing the forcing F at the boundaries, which gives the coefficient C of the potential expansion in every subdomain, and that fully determines the wave field. Next, we build in a breaker parameterization based on strain. Once the wave field is known in the domain, the strain undergone by each ice flow can be evaluated. In a given flow, if the strain exceeds in absolute value some prescribed threshold, the flow is said to break where this strain was maximum. In practice, it means that we allow a flow to break in no more than 2 pieces. Now for what comes next, it's useful to have in mind that the strain profile along a flow depends on the phase of the wave at the flow edge. Different phases will lead to different locations of the maximum strain, which translates to different sizes for the broken pieces. The figure shows the strain envelope for a semi-infinite flow in blue, and 4 strain profiles for 4 equally spaced phases between 0 and pi excluded. The blue tick at the top shows the location of the maximum strain for the envelope, and the orange ticks show the location of the maximum strain for each one of these phases. So depending on the phase, for the same forcing, our model will yield different breakup location, which results in different flow lengths. So this is the outline of the numerical experiment we ran. The idea was really to highlight the effect of waves on the flow size distribution, so we ignore all other processes affecting the ice. We let a distribution emerge by repeatedly factoring flows of a semi-infinite ice cover covering the right end of the domain. At each iteration, the wave field is computed for the current geometry and the prescribed forcing, and the strain along all the flows is computed. It is then compared to the critical strain, and all the flows that should break are identified and split into the 2 parts. The resulting array of flows is composed of newly broken flows and flows that did not break. Now, to avoid overlapping of the flows in the domain, and because we neglect drift and all kind of ice motion, we reposition them at new random locations while preserving their order. And as I just mentioned, the size of new flows after another cycle of breakup will depend on these randomly assigned locations, which control the phase of the wave when it reaches the flow. So I ran the model several times in the same configuration to average out the resulting distributions, where a configuration is a set of physical parameters such as the ice thickness, the wave amplitude, period, and strain threshold. We're interested in the steady state solution, so we run these experiments until the wave can no longer break any flow in the domain. Here are some results. Histograms showing the resulting flow size distributions for various critical strains on the left and various ice thickness on the right. So these histograms are, as I just mentioned, averaged over different realizations of the same configuration. The other parameters are kept fixed and their values are mentioned on the slide. The first takeaway is that we get all these distributions are race skewed with a lot of smaller flows compared to the larger flows. Changing the critical strain mostly shifts the distribution and preserves its shape, while reducing the thickness leads to a relative increase of the number of smaller flows and thins the distribution tail. Another visualization of the distribution for all of these dots represent a median flow size, and the colored areas around them, the interquartile ranges around these medians. So for increasing critical strain on the left, there isn't much evolution in the width of the range, but there is for increasing thickness on the right. So what it means is that we get less peaked and more spread out distributions, like we showed on the previous slide. Colors indicate the wave period, so shorter waves lead to smaller flows and also less spread out distributions. And this is the number of flows at the end of the simulation, which is a proxy for breakup intensity. And we can see that it depends sharply on the wave period. Breakup is only effective in a limited period band. with shorter waves being effectively reflected by the ice edge and longer waves not able to bend the flows enough for them to break. So actual oceans are not monochromatic. So to extend these results, we combine these distributions by giving them weights corresponding to a wave spectrum. There's a lot of different parameterizations for ocean wave spectra, and here we are just using a Pearson-Moskowitz spectrum, mostly because it can be easily parameterized to depend only on the significant wave height, which is just twice the amplitude for monochromatic waves. When the wave height increases, the peak frequency of the spectrum shifts toward longer waves. And as we just saw, longer waves, intermediate length waves are effective at breaking the ice. So after setting a wave amplitude, we sample the spectrum and give to all of the monochromatic distributions weights to obtain a polychromatic distribution. The result is again right skewed. And because earlier we run the model several times for each frequency, and we use 200 frequencies to discretize the spectrum, it gives us a lot of different ways to combine the monochromatic distributions together. And this histogram is an average of 500 of these combinations. And so to each one of these 500 datasets, I fit a long normal distribution. So random variable is long normally distributed if its logarithm is normally distributed. The distribution has 3 parameters, including a location shift. There is some dispersion between the fits, especially around the mode of the distribution, so where the most common flow size is located. But they are in good agreement with one another and a good fit to the data. The linear combination of long normals doesn't have a closed form. So instead of averaging the distributions themselves, we average the parameters to get a mean distribution, which represents pretty well mean histogram that I displayed. So to qualify the goodness of fit, we can compare the cumulative distributions of the data, so here in black, to the long normal model in blue. And again, there is a good agreement between the two, since as one moves towards the right of the figure, the observations become less and less frequent, 99.9% of them being above this 10 to the negative 3 tick. Basically, what our model does is, what the long normal model does is over-predicting longer flow sizes that do not exist in our physical numerical model. And this representation of the cumulative count is often used in flow size distribution observation studies. And we would like to make the point that the long normal distribution with its gradual bending is comparable, at least qualitatively, to some observations that suggested split parallels for the data. So I applied this analysis to a variety of scenarios. For simplicity, only varying only one parameter at a time with respect to the configuration I just showed you. So all of these, so these are the physical parameters, and in all of these cases, the flow distributions that we get are well fitted by a long normal with these parameters on the y-axis. And these parameters can in turn be used to generate samples without the cost of having to run the complete numerical model. So this figure shows what forecasts could look like for each value on the x-axis. corresponding to different ice or wave conditions. The y-axis shows a range of flow sizes that the long normal model will predict. So 50% of the flows will be within the light stripe, 95% of them within the darker stripe and lighter, and 99% of them in the darker stripe and lighter. So being able to make this kind of prediction will be useful to generate subgrid flow sizes when running a large-scale CIS model coupled to a wave model to represent the effect of processes impacted by flow size and not just ice concentration. You can find more details in our paper currently under review in the cryosphere. And we are currently working on alternative parameterizations of the C-state to evaluate the robustness of the long normal model. So I'll leave you a summary to read, and I'll take your questions.
Thank you very much. And thanks for keeping so well to time. Is there some questions here? I can't actually see who's got their hand up, so just unfortunately, I'm not quite sure why that is, but someone's clapping, which is great. Yeah, Ellie, do you want to go forward?
Yeah, well, first off, really good presentation and really good article. Also, I started to read it, and it's